In this part of the lecture, I'm going to cover some of the characteristics and basic analysis tools and some key elements when it comes to designing and operating arterials or traffic signals, which is usually represented in the literature as interrupted flow. So as opposed to uninterrupted flow, which we're mainly focusing on freeways and expressways with no traffic light or no roundabouts, etc., interrupted flow is a flow of traffic where it gets continuously or regularly disrupted by incoming and exiting cars. It gets disrupted by signalized intersections or roundabouts or driveways, etc. So in this lecture, I'm going to more focus on signalized intersections, but interrupted flow is not just limited to signalized intersections. For example, an intersection with a stop sign or a yield sign or a roundabout, all of that could be considered as interrupted flow, and it has its own analysis tools and things to consider when it comes to understanding and designing or operating them. So signalized intersections operate with the assistance of a traffic signal, obviously, and they periodically or cyclically assign the right of way to a movement or combination of movements. Ideally, the amount of time that is allocated to each movement or combination of movements aims to minimize the total travel time or total delay or the number of stops at the intersection, and tries to allocate the capacity optimally. So when it comes to designing the signal intersection, other than the geometric aspect of it, that sure, we look at the geometry of the intersection, how many lanes do we have, what movements do we want to have on the intersection, do we want to have a right turn or left turn lane specifically, what kind of movements do we want to group into each other. The way we need to design the signal timing itself is a very important problem. How much green time should we give to approach 1? How much green time should we give to approach 2? What should be the entire length of the cycle of a traffic signal that goes from red to green? All of these questions falls under this designing signals, which we cover to some extent today. So let's start with some key terminologies in for signalized intersections. The main term that I'd like to introduce is cycle length, which we usually represent by capital C. Cycle length is the length of time required to go through all the signal indications at the signalized intersection and serve all movements in all approaches. And it usually takes 60 to 120 seconds. Although sometimes much longer cycles are provided at some complex intersections, but the typical length of a cycle length is between 60 to 120 seconds. Phase is another term that we usually use when it comes to designing signals, and it is the part of a cycle serving one movement or one group of movements, and it includes green, yellow, and all red intervals. The other term that we use is interval. Interval is the part of the cycle where all signal indications remain the same, which obviously we have green, yellow, and all red intervals for most phases. We also have change and clearance intervals. Change interval represents the yellow time, and clearance interval represents all red interval, which are used for transition between the right of way, the assignment of the right of way to the next phase. The yellow interval is usually represented by capital Y, which is provided to warn the approaching drivers that the signal is about to change red, and its duration is a function of the approach speed, mainly usually 2 to 4 seconds. And the all red interval is but the all red interval is relatively short. It's usually 1 second. If the intersection is very big, it goes to 2 or 3 seconds. And usually the reason we provide all interval is to ensure the intersection is cleared from all the vehicles that are going through the intersection before the right of way changes. The length of all these intervals is set to ensure we have a safe operation at the intersection. We want to avoid crashes, right? So that's why we have yellow and all red intervals. We have another term called green time, which we usually represent with capital G, and that is the part of the phase when the respective movement or movements are given the right of way. It should be set to minimize the travel time or delay throughout the intersection, considering all the demands from the conflicting movements at the intersection. We also have a key term called lost time, or LP, which is the part of the phase that is essentially not used by any movement, and that's why it's called lost time. It consists of the startup lost and the clearance lost time. The startup lost time, it's usually called L1 or LL, is the lost time experienced by vehicles at the beginning of the green, and the clearance lost time, or LC or L2 here, is the lost time experienced at the end of the green time when vehicles do not use some portions of the yellow and all red intervals. I'll show you a graph in a minute describing more about describing all these concepts in a more visual way. We also have a term called effective green time, which we usually represent with a small g, which is the part of the phase effectively used by the respective movement or group of movements, considering the lost time experienced at the beginning of the cycle. So capital G was the total green time minus the lost time. It gives us the small g, which is the effective green time. That is, it is the time that is really effectively used by vehicles. So look, here's an example of or an example visualization of what intervals, effective intervals, and lost time for different phases actually mean. So we have phase 1, we have phase I, and different intervals. So each phase has different intervals. We have the green interval, we have the yellow interval, and we have the all red interval. We also have this red signal indication at the end, where the movement of this specific approach is totally stopped. And now if I want to introduce the effective intervals rather than the, so capital G and capital R are green time and red time, but we also have a small g and a small r, which are the effective green time and effective red time. So at the beginning of the green time, we usually have some lost times. And at the end of the green time, within the yellow time, we also have some lost time here as well. So not all people use the available yellow time to pass the intersection. So we have the startup lost, we have the clearance lost. So the total lost time, so R is actually effective red light, is actually the red time. Effective red time is actually equal to the nominal red time plus the total lost time, while small g, or the effective green time, is the capital G, the nominal green time, minus the total lost time, including the startup lost time and the clearance lost time. So this is the startup lost time, and this is the clearance lost time. And cycle length is actually the summation of C is actually the summation of a small g plus a small r, or C is actually capital G plus capital R plus capital Y. So the summation of the green time plus red time plus yellow time gives us the cycle time. And here's an interesting graph to look, where it shows how the flows changes, how the traffic flow changes when the light turns to green. So x-axis is time, y-axis is the flow of the intersection, or one approach, basically, the flow rate of an approach. So when it is red, when the light is red, of course there's no flow, it's zero, right? But as soon as the light turns green, we see a little bit of a lost time because it takes time for vehicles to react, to accelerate, and start moving, right? So we have this startup lost time at the beginning, and then the flow gradually starts increasing until it reaches something that we call saturation flow, which is the maximum discharge flow from the intersection. And then it could continue with the saturation flow, or because if the demand or if the arrival rate is slowing down, the flow goes down, it may go, and then at the end, when the light turns yellow, not necessarily everybody is using the whole 2 or 3 seconds of their yellow time, right? So some vehicles decide to stop at the yellow time, so for safety purposes. So we can see that suddenly the flow starts dropping before the red time appears, red light appears, right? So we also have this small clearance loss time at the end. And therefore, again, if I write it again, G plus startup loss time plus clearance time gives me the capital G, or the nominal green time. I think I just talked about this, that a small g is the green time. Actually, what I have missed here is actually the yellow time. I should have added the yellow time here as well. So G plus L plus L2 is actually green plus yellow time, because yellow time gets embedded into it as well. So if I want to do it correctly here, effective green time is equal to the nominal green time plus the yellow time minus the total loss time, including the startup loss time and the clearance loss time. And if you just replace that with the total loss time, so effective green time is capital green plus yellow time, don't forget this yellow time as I did, minus the total loss time. Okay? And again, as I said before, cycle length is actually equal to capital G, capital yellow, and capital red. Or I can replace that when it comes to effective green time and effective red time, then there's no yellow, right? Because it's either red, it's either effective red or effective green. So cycle lengths, so this is cycle lengths, could be G plus R as well. Or another way, it's capital C minus effective green time gives us the effective red time. But what is discharge flow? So to understand discharge flow or saturation flow, let's have a look at this time and space diagram where light is green, vehicles are moving, it becomes yellow, and then suddenly red, so vehicles stop. And then as soon as it becomes green again, it takes a bit of a time for vehicles to start accelerating and move, right? So, and if we measure the headway between these trajectories or vehicles in this time and space diagram and plot them here. So x-axis is the number of the vehicle in the queue. So it's the number of the vehicle in the queue. And y-axis shows the headway. So y-axis shows the headway. So vehicle number 1 usually has a large headway because it takes a bit of a reaction time and time to accelerate and move. Same thing with the second vehicle and the third vehicle. So the first few vehicles in front of the queue at the signal, they usually have larger headways when the light turns green. After the first few vehicles move, we'll see a more stable pattern in the headways, where headways remain roughly the same for the next couple of vehicles until there's no demand. And this headway, this stable headway here, which remains the same for after the first few vehicles, that's what we call saturation headway. So if the headway is small, flow is large, right? Because flow was the inverse of headway, if you remember, right? But the first few vehicles, because there's reaction time involved, there's loss time involved, etc., they usually have larger headways than the actual saturation headway. But after a few vehicles, we'll start observing the saturation headway. So if we only look at this stable part of this diagram, where vehicles have more stable headway, we can take that as saturation headway. And we can use that equation that flow is inverse of average headway to calculate what is the saturation flow. So this S is our saturation flow, which would be only 1 over the average headway. And because here is in seconds, we're talking about seconds. If you want to convert that into vehicle per hour, we just need to multiply that by 3,600 to convert that to vehicle per hour, right? So that's how we get saturation flow, by observing the saturation headway. Let's now introduce something called intersection capacity. So intersection capacity is usually represented by a small c. Again, look, capital C is the cycle length, small c the intersection capacity. So don't mix them up, please. So small c, or the intersection capacity, is equal to the saturation flow multiplied by the ratio of the available time for vehicles to move for that approach, which can be calculated by the ratio of green over the cycle length. This is capital C here. So this G over C ratio is the effective green time divided by the cycle time. So this is the effective green divided by the cycle length. It gives us the available time for that approach for the vehicles to move, right? So if we multiply this G over C ratio by the saturation flow, we can actually calculate the capacity of the intersection. Let's go over an easy example. So we have a series of vehicles who are discharged from a signalized intersection approach in the following figure. I want to go over the figure I'll go over the figure in a minute. Where the vehicle's departures are represented by the vertical lines along the x-axis, which is time. The cycle length at the intersection is 100 seconds, so capital C is 100 seconds. At the beginning of the green time, there are 10 vehicles queued up, as shown in the figure, which we're going to see. The volume during this green time is 16 vehicles divided by, let's have a look later that what is the time window. Determine the saturation headway, saturation flow, a startup loss time, and the capacity of the approach. So let's have a look at the figure to see what data we've collected. So x-axis is time. So this is time. This is the start of the green. The first vehicle departs at time equal 4 seconds. The second vehicle departs at time equal 8 seconds. The third vehicle departs at 11 seconds. Fourth vehicle departs at 13. Fifth vehicle departs at 15. And this will continue until the 10th vehicle departs at 25 seconds. And then you can see that the headway between, so the horizontal distance between each vehicle represents the headway here, right? Because headway is the time between the vehicles. And then we can see the demand slows down a little bit, and then that's why headways becomes large. Then we have 11 vehicle, 12 vehicle, and 13 vehicles. And this would be the end of the green time. So what would be the saturation headway here? So I want to calculate the saturation headway here. If you look at the headways, let's calculate the headways. So So this is from 4 seconds to 8 seconds, it's 4. From 8 seconds to 11, it's 3 seconds. And then from 11 to 13 seconds, it's 2 seconds. It's 2 seconds here from 13 to 15. So, and you see it remains 2 as well. So it remains 2. It remains 2 until the vehicle number 10. And then it goes to 3 again, and then 28, that's 6 seconds. And then this is very large. It's 8 seconds, and so on and so forth. So remember we said the first few vehicles in the queue, because of the reaction time, because of the lost time, they need to accelerate, etc., they don't necessarily represent the saturation headway. But when the headways become stable, you see, here is the part that the headways become stable. The headways becomes 2 seconds. So this 2 seconds, I can take this saturation headway as 2 seconds here, because that's where the vehicles actually start having a stable headway, right? So that is my saturation headway. I can then calculate the saturation flow, which is 3600 divided by 2 seconds. So that would give me 1800 vehicle per hour. So that was my saturation headway. This is my saturation flow. What else the problem was asking? So we calculated saturation headway, we calculated saturation flow. Let's calculate the startup loss time, and then we'll go to the capacity. How can I calculate the startup loss time here? So we have this saturation flow, right? Or sorry, the saturation headway of 2. So if all these 25 vehicles that were in the queue were able to move with that headway of 2 seconds, that would be 25 multiplied by 2 seconds, right? So if all these, sorry, not 25, all these 10 vehicles, we have 10 vehicles in the queue. So you see, after this point, there's no queue. The demand goes down and vehicles start arriving with a large distance, time distance. So I have 10 vehicles in the queue. And the problem was also saying that there are 10 vehicles in the queue. So if all these 10 vehicles were able to go through the intersection with the saturation headway, that means it should have only taken them 20 seconds to go through the intersection. However, we can see that in reality, it took them 25 seconds to go through the intersection. So that means there is 5 seconds of lost time here. So this 25 minus 10 multiplied by 2, 20, gives me the 5 seconds lost time. So this 5 seconds is actually the lost time. So this 25 minus 10 multiplied by 2, which is equal to 5 seconds, is my lost time. And if I want to calculate, so that's my lost time, right? Which is the startup lost time. And next is the problem is asking for the capacity of the approach. If I want to calculate the capacity is saturation flow multiplied by G over C, right? So I need to get this a small g. So a small g is capital G minus the lost time, right? And here we calculated that the green time was 68 seconds. How did I get that? I think 68 seconds is here. That's the end of the green time. So 68 seconds minus that 5 seconds of lost time gives me 63 seconds. So that's my small g, or effective green time. And if I want to calculate the capacity of the intersection is 1800 vehicle per hour multiplied by 63 seconds divided by, what was cycle length? The cycle length was given as 100 seconds. 63 divided by 100 multiplied by 1800, this would give me the capacity, which is equal to 1,134 vehicle per hour. There's also an alternative method to estimate the capacity, and that is by multiplying the number of cycles within the hour that estimate the capacity per cycle and multiply by the number of cycles per hour. Again, I don't really like this approach. I mean, I prefer the first approach, which is very intuitive to understand. We calculate a small g, we calculate the saturation flow, and then we calculate the capacity from that. But there's another alternative method here that you calculate this C per cycle, which is the effective green time divided by the saturation headway. So this means 31.5 vehicles per cycle will go through. And then if you want to convert that to vehicle per hour, you just multiply that by 3,600 over 100, and then you get that the same number. So you see it's the same number. But as I said, I think the first approach is more intuitive and more it's easier to interpret physically, at least for me. So in the next part, I'm going to connect the operation of the traffic signals with the arrival and departure curves cumulative plots. So an easy way to understand and analyze how delay at a traffic signal is calculated is to visualize it in a queuing system and plot the cumulative plots of the arrivals and departure. So if this is my time, and this is the number of vehicles that are passing through it, and here is my green, here is my red, then it becomes green. And if this blue curve is my arrival, and this light blue or light green is my departure, as we covered before, the area between these two curves, it represents the total delay at the intersection. So the total delay at the intersection can be calculated by estimating this area between the two curves. How can I estimate the area between these two curves? So the area between these two curves would be the integral of A from whatever time we are interested in, from T1 to T2, minus the area underneath D from the same time, same two. So if we take the integral of A then minus the integral of D, it will give us the area between these two curves, right? And then as I said before, if I want to calculate queue length or the number of vehicles in the queue at any time, the vertical line between these two curves represents that queue length. So at this time, this would be the queue length or the number of vehicles in the queue. And if I want to calculate what would be the delay for any specific vehicle at the intersection, if I take this vehicle and if I calculate the length of this horizontal line, that gives me the delay for that specific vehicle. And then if you look at this queue clearance time here, let me see, what is this? How long it takes for the queue to dissipate or to totally recover or clear at this intersection. So at this time, the queue starts forming, right? You see the queue forms, it grows, it gets to the maximum point here. So that's the maximum queue, right? So that's the maximum queue length. And then it gradually shrinks until this point. So from it, the queue starts propagating from this point and it dissipates in this point. So that's why we call this point, sorry, this should have been here. This point is the queue clearance point or time. And here is actually the queue start or queue forming time, where the queue starts actually forming. And now if I want to calculate the total delay in each cycle, so how can I do that? I mean, instead of taking the integral, there's another easy way to do it, and that is using triangles. Again, remember I told you the importance of triangles in traffic flow theory? So if I have this arrival and departure curve, and if I want to calculate total delay, I just need to calculate this area, right? Which is actually a triangle. And that would be the area of the triangle is half of base multiplied by the height, right? So the base of the triangle here is this red time, and the height of this triangle is actually the number of vehicles in the queue. So it would be half of R multiplied by the number of vehicles in the queue. That gives me the area, that gives me the total delay for that intersection. But how can I get this ND? To get this ND, I can look at another triangle actually. So let's first calculate the red time. So here we say red time is the cycle length minus the effective green time. And then I can actually rewrite this to be like C1 minus G over C, right? It's just a different way of rewriting. So I have the red time here as a function of the cycle length and G over C. Sorry, again, this is not G over C. Yeah, that's G over C, yes. So this is all the cycle length. There's no capacity here, okay? So it's a cycle length. This is also cycle length. So if I come back to this one, so we looked at this triangle. I can actually draw another triangle here. So if I erase this triangle here, and if I look at this other triangle, look at this triangle here. There is this bigger triangle here, right? So what would be the area of this triangle? This area of the area of this triangle, remember this point was, we call this the Q clearance time, QC, right? So the area of this triangle is actually so this area is actually half of the ND multiplied by what? It would be multiplied by this length, whatever that length is, right? It would be, if we consider this as 0 here, so it would be multiplied by QC, right? There's also another small triangle here. So it's a lot of triangles. So we can play with lots of triangles here to do the analysis we want to do. So there's also this little triangle here. And then this part here is actually QC minus red time, right? So the base is QC minus red time, height is ND. And now let's go back to this. So how can we get this ND? We said we want to know what is this ND is. So ND is if the arrival rate, so we know the slope, if we know the slope of this line, which is the arrival rate, right? Let's call that V here, or A, whatever you want to call it. So so the arrival rate, the slope of that line, the slope of the arrival curve is actually equal to, remember we said the slope is rise divided by run. So in this case, it would be the rise, which was ND, divided by R plus QC. I think the way I've calculated here is that this is considered to be QC. This little part here, this section is called QC here. I could have called it something else, but I mean, this is QC here. So if I look at this larger triangle, the slope of this line is ND divided by R plus QC, right? So therefore, ND is equal to that arrival rate multiplied by R plus QC. So I have ND here. And now, if I want to estimate QC, We use the observation that R plus QC, the total number of vehicles arriving, is equal to the number of vehicles departing. So something like the conservation law, where the total number of vehicles that are coming should be equal to the number of vehicles that are leaving, right? So ND equal ND. So the first ND comes from the arrivals, which we said arrival rate multiply R plus QC. Now, the vehicles that are departing, these are the vehicles that are departing, would be the saturation flow. This is the saturation flow. Multiply that time window that vehicles are leaving. So it would be QC. And now if we put this together, we'll get this QC as a function of the red time, saturation flow, and the arrival rate. So QC would be R divided by S over V minus 1. So that's how we get the Q discharge point. And then if you want to calculate, now that we have all these values, we have QC, we have ND. If I want to calculate the total delay, I need to calculate, the total delay was this, right? 0.5, half of R ND. So now if I just put everything into the calculation of the total delay, so this was R ND, right? If I calculate that area, I would be able to get this total delay formula. And then if I want to calculate the average delay per vehicle, the average delay per vehicle is simply total delay divided by the total number of vehicles. If you do that, if you do the math, if you divide this by the total number of vehicles in the queue, which is actually ND, right? If you do the math, you'll get to this little formula, which is known as Webster's delay formula. So I did all of that to get to this point. So this Webster's delay formula is one of the most basic formulas in designing traffic signals, which gives us the average delay per vehicle as a function of G over C, as a function of the arrival rate, as a function of the saturation flow. So if we have the saturation flow, if we have the G over C, if we have the cycle length, if we have the arrival rates, we can actually calculate what is the average delay. So if you want to design a traffic signal that minimizes the average delay per vehicle, we can simply play with the G over C ratios and try to minimize and reduce this average delay by just using this little formula. Again, this only is used for specific intersections, very simple intersections. If the intersection is a little bit more complicated, the arrival rates are not constant, this formula does not necessarily hold. We have more complicated formulas for that, but the essence of the analysis is the same. So we all look at this arrival and departures. We try to use triangles and the slopes and everything to calculate the total delay and the average delay, and then try to minimize that by choosing the appropriate green time, by choosing the appropriate cycle lengths, etc. We have two concepts here. One is called undersaturated signals and oversaturated signals. Just like this example is a good example of undersaturated traffic signals. Why? We call it undersaturated because actually it's not an undersaturated signal, is it? Yes, it is. Because the queue can dissipate before the red time. So you see a queue forms, and then as soon as the green time starts, the second green time starts, the queue will totally dissipate and recover before the end of the green time. So if green time is enough to totally discharge all the queue, we call that an unsaturated signal. But if the green time is not enough, or maybe the demand is so high that the queue will not dissipate within the available green time, we call that oversaturated signal. So look, this is the departure curve, this is the departure curve, the green time finished, but we did not intersect. If it was an undersaturated signal, we would have done it this way. But because the departure curve is not intersecting the arrival curve, so there is this little part which is called residual queue that is left. So I'm sure this happened to many of us, that green time comes, you go, but you're unlucky. You have to wait another total cycle length to leave the intersection. And you will be that residual queue then. So at the end of the green time, the queue will not dissipate entirely. So these vehicles have to wait, unfortunately, and then they go. And then you can see oversaturated signals are a terrible thing. They have such a large total delay. That's a killer for urban traffic. And you can see that in the time and space. Sorry, you can see that in the cumulative plot, as I just quickly described that. But anyways, I'm done. So thank you very much. Sorry if it was a little bit too fast today. I had a lot of things to cover.